A net torque causes angular acceleration. If there is an angular acceleration, then the angular velocity is changing. So we can rewrite our formulation of Newton's second law for rotational quantities in terms of a change in angular velocity. So an angular acceleration is a change in angular velocity with time. If we multiply the I over the delta omega, we get the I omega final minus I omega initial. Now we can let I omega be equal to a quantity which we label L, and this quantity is angular momentum. So the symbol L is used to represent angular momentum, and we see then that a net torque causes a change in angular momentum with time. This is just like the equation we saw in linear land, where a net force is equal to a change in ordinary momentum with time. So we get the same exact expression, just with angular quantities. Now, if the net torque is zero, so if the torque from outside forces is zero, then angular momentum is conserved. There is no change in angular momentum. The final angular momentum is equal to the initial angular momentum. And this means we can write down I initial omega initial is equal to I final omega final. So if there is some change in the way the material is distributed, if there's some change in how the mass is distributed about the axis of rotation, then that will cause a change in the angular speed. So if I decreases, then angular speed will increase. And one example of this is the ice skater. So you've probably seen ice skaters who rotate, and they can change the rate of their rotation by bringing their arms inward. So initially, an ice skater's arms and legs will be far from her center of rotation, and she will be rotating slowly. As she brings her arms in, she decreases her moment of inertia because more material is closer to her axis of rotation, and as a result, her rotation speeds up. I goes down, so omega increases. You can also see this in this classic physics experiment, where a student is sitting on a chair with a couple of weights. Initially, she holds the weights far from her body and far from her axis of rotation, and she is rotating slowly because her moment of inertia is large. Then as she brings the weight in, her moment of inertia goes down, and so her rotation rate increases. This is another classic physics experiment where you have a rotating wheel. Initially, the wheel is held so that its angular momentum is to the side. That is, if you wrap your hands around the axle of the wheel in the direction that the wheel is rotating, your thumb will point in the direction of the angular momentum vector. So the angular momentum vector initially is off to the side. Then when the student tilts the wheel, the angular momentum vector is pointing up and down. It's pointing either upwards or straight downwards depending on how the wheel is rotating. So since there is now vertical angular momentum, the student must begin to rotate to conserve angular momentum so that the net angular momentum of their body plus the angular momentum of the wheel is zero in the vertical direction. So initially there is no angular momentum in the vertical direction. He tilts the wheel, so now there is angular momentum in the vertical direction. So then he starts rotating in the opposite direction to conserve angular momentum in the vertical direction.